So welcome to this fifth lecture in electric circuit analysis, and here in this lecture we are going to discuss the inductors and the capacitors. So previously what we were doing is that we studied circuits that are composed of resistances and the sources. So these resistances and sources together makes to be a DC part. So we were discussing only the circuit that were DC, comprising of resistance and the sources. Now, in this particular lecture, we will focus our discussion on two additional circuit elements. What are they? One is the inductor and another is the capacitor. It means that inductors and capacitors, when it will come to the circuit, obviously the introduction of AC will come. So, whatever the discussion we have done till now, where for the DC circuits, now we are going to discuss for the AC circuits. So resistors, as you know, it convert the electrical energy into heat. So inductors and capacitors are energy storage element. It is not energy dissipating element like a resistor. So resistors will convert the heat energy into heat. So it is an energy dissipating element. On the other hand, inductors and capacitors are basically energy storage element. They store energy and then later return it to the circuit after a certain point of time. They do not generate energy. Now it is a very important point to be noted that inductors and capacitors do not generate energy. The energy that has been put into these elements can be only extracted. That is the reason inductors and capacitors and together with resistors, we set them to be the passive elements and not the active elements. Active elements are those elements which can generate energy like a voltage source or a current source. But here inductor and capacitor will not generate energy. It will only store the energy and later the energy will be extracted. Thus, like resistors, they are said to be the passive elements. So inductors and capacitors are basically the passive elements. Now, there is one subject which is electromagnetic field theory. You people have studied in the 12th standard also, which is the basic approach to the study of the effect of electric charge. So when we talk about the electric charge, then electromagnetic field theory is the subject, that is the basic approach. Circuit theory is just the simplification of the field theory that is much easier to apply. So when we simplify the electromagnetic field theory, we comes to circuit theory in terms of understanding. Now, what is the capacitance? Capacitance is the circuit property that accounts for energy stored in the electric field. So whenever you have an electric field and the energy is stored, that property of the circuit is known as capacitance. On the other hand, inductance will store the energy in the magnetic field. So electric field and magnetic field together makes to be electromagnetic field theory. So in electric field, energy stored is being done by capacitance. In the magnetic field, energy is stored by the inductance. The voltage across an ideal inductor. Now when we talk about an ideal inductor, it means there is no loss in the inductor. The inductor is pure ideal and there is no resistive component. So resistive component is not there in the inductor. So the voltage which is across the inductor is proportional to the time derivative of the current. So whatever the current is flowing here, so the voltage will be the time derivative of the current. So when we talk about di by dt, it means that current is a function of time. Also, voltage is a function of time. So the function of time we have not discussed when there was a resistance, because the resistance is a constant property which is not changing with time. So the voltage which was we discussed I into R, there the voltage is constant because we talk about the DC quantity and there is no change. Now in inductors and the capacitors, the voltage will change with respect to time. So the voltage across the ideal capacitor is proportional to the time integral of the current. So either we will be having integral of I dt or we will be having di by dt component when we talk about the capacitors or we are talking about the inductors. So now we have to deal with the differential term or the integral term to determine the voltage. So apart from inductance and capacitance, one more property we are going to discuss, which is known as the mutual inductance. So mutual inductance is that property of the circuit that accounts for magnetic field that are mutual to several inductors. So when we have too many inductors and they are connected in either way, then the inductance which is common between the inductance is known as the mutual inductance. So it is that property of the circuit that accounts for magnetic field which is mutual or the common between the several inductors. Mutual inductance is basically the main phenomena that will be occurring in the transformers, and it is very critical to the transmission of electric power over a long distance. So mutual inductance is very important, and this is based on Faraday's law of electromagnetic induction. So there we especially in transformers we study mutual inductance in D. And other several type of transducers. So when we talk transducers, it is basically means sensors. So when we have sensors and the transducers, the inductance and the capacitance properties are severely used. So when we have inductance and capacitance, they can be connected and form different type of sensors. Sensors may be humidity sensor, temperature sensor, and so on and so forth. Now we'll start our discussion what is a capacitance, and then we discuss for inductance. So a capacitor is a passive element because it is an energy storage element which is storing energy in the electric field. So when there is an electric field and you store the energy with a element, that is known as a capacitor. Capacitors are constructed by separating two sheets of conductor. So basically we will be having two conductors. So two conductors will be there and which are usually metallic. So these two conductors are basically made up of some metals, and there is a thin layer of insulating material which is separated by this conductor. So insulating material will be in between the two conductors which are usually made up of metals. So when we talk about a parallel plate capacitor, so you know the formula for capacitance is epsilon A by D. This has been taught in the 12th standard. The sheets are basically flat and parallel. So when we talk, this is the parallel plate. So first plate is here and the second plate is here, and between that there is a dielectric. So dielectric is something which is insulating in property. Plates are conducting. So plates are conducting and the dielectric which is filled between the two plates are basically insulating. Now these dielectric which is filled between the two conducting plates is defined with a property which is known as the permittivity. So permittivity is the property which defines how the quality of the dielectric is there. And the other, when we say the formula for the capacitance which is epsilon A by D, so we can see that area and the distance of separation between the plates play a very important role in deciding the capacitance. So capacitance is basically a function of epsilon, which is the permittivity of the material, the area of the plates, and the distance of separation between the plate. So if you change any of the quantity, the capacitance will change. So when we have the area to be more between the plates, the capacitance will be more, and when the distance between the separation is reduced, capacitance is also more. If the permittivity is high enough, then the storing energy will be better. Now when we apply a voltage source to the conducting plates, then charge gets separated out and the current starts flowing in the network. The insulating material which is between the plates is known as the dielectric. So dielectric which is filled up between the conducting plate, it is basically the insulating material. And some insulating materials are air, polyester, polypropylene, mica, or a variety of other materials. So these type of materials are generally used when we talk about the dielectric. Capacitors are used extensively in electronics, communications, computers, and power systems. So different fields of electrical energy or computer energy also we can say their capacitors are being used. Now we'll discuss the capacitance of the parallel plate capacitor a little bit. So when we talk about the capacitance of a parallel plate, as I said, there will be two conducting plates, 1 and 2, and the area of the plate A will be given by the length into width. So L is basically the length of the plate and W is basically the width of the plate. D is the separation between the two plates. Then the capacitance is given as epsilon A by D, where epsilon is basically the permittivity of the dielectric material, also known as the dielectric constant. So dielectric constant and permittivity are the same thing, and area and distance of separation. When we talk about a dielectric which is vacuum, then the value of epsilon we take at epsilon naught. So epsilon naught, which is the dielectric constant of vacuum, is 8.85 into 10 to the power minus 12, and the unit is farad per meter. Any other material which is acting as a dielectric, so that value of the permittivity will be taken with reference to the vacuum. So with reference to the vacuum, the other dielectric material will be defined, and there is a constant which is used, which is epsilon r, means the relative dielectric constant. It is unitless. There is no unit for this. The unit of epsilon is farad per meter. So you will be having farad per meter here because epsilon r is unitless. So if you take some values of the dielectric like air, the value is 1, because when we talk about the vacuum, it is 8.85 into 10 to the power minus 12. So for air, epsilon r will be 1. Diamond 5.5, mica 7, polyester 3.4, quartz, silicon dioxide, water. You can see for a water, the dielectric constant is near to 80. So these you can remember. For a water, the dielectric constant is near to 80. This value is very important, which either will be provided in the question or you have to remember it. So the dielectric constant of vacuum is 8.85 into 10 to the power minus 12. Now, in order to understand the capacitance, we will take it to the fluid flow analogy to understand what is the capacitance going on. What is the phenomena of the capacitance? So in the capacitance, you have two conducting plates 1 and 2, which is separated by a dielectric material. Now if these conducting plates is connected to a source, which is a voltage source, if it is connected to this, then what will happen when the voltage source will be connected? Then in that case there will be a flow of the current. So you know that this will be a positive terminal, if and this is negative terminal we can take, and current flow from higher potential to lower potential. So there will be a flow of the current. You also know that the electron flow will be opposite in direction to the current flow. Now we will try to understand these capacitance property in electrical field to the fluid flow analogy and try to understand what is going on. So suppose the current in the capacitor is flowing downward. Now this is with reference to the voltage source that has been added. We take an example that current is flowing in the capacitor in the downward direction. Then what will happen? Since the current is due to the flow of electrons which is moving, conventional current flowing downward represent the electron moving upward. So electron flow will be in the upward direction, current flow will be in the downward direction. This is the general notation. So as electrons move upward, they collect on the lower plate of the capacitor. So when we take the lower plate of the capacitor, then there will be the electron deposition. Thus, the lower plate accumulates a net negative charge that produce an electric field in the dielectric. So these dielectric, there will be electric flux lines will be generated due to the negative charge which is at the lower plate. The electric field forces the electrons to leave the upper plate at the same rate that they accumulate on the lower plate. So the phenomena in the lower plate and the upper plate both will occur at the same rate, and there will be the movement of the electron. Therefore, current will appear to flow through the capacitor. Now it will be looking like there is a flow of the current through the capacitor. As the charge builds up, voltage appears across the capacitor. So when the charge will be building up, then there will be a voltage developed. we say that the charge accumulated on one plate is stored in the capacitor. We generally say this, that when there is a charge accumulated in one plate, the energy is being stored. However, the total charge on both the plate is always zero, because positive charge on one plate is balanced by the negative charge of equal magnitude on the other plate. So you have seen that there are two plates, 1 and 2, and both are having opposite charge. One is negative and another is positive. So the total charge, if you take, that will be coming to zero, because there will be a balancing of the positive and negative charge. Now these, if we understand in terms of fluid flow analogy, a capacitor represents a reservoir with an elastic membrane separating the inlet and outlet. So in the reservoir, there will be an inlet from which the water will enter, and there will be an outlet from where the water will go out. And this is an elastic membrane. So as the fluid flows into the inlet, the membrane is stretched, creating a force. Now this force which is exerted on the membrane is analogous to capacitor voltage that will oppose the further flow of the liquid. The displaced fluid volume starting from the unstretched membrane position is analogous to the charge stored on one plate of the capacitor. So as we can see that in the fluid flow, there will be an opposition to the flow of the force will be developed, and there will be opposition to the further flow, that is analogous to the capacitor voltage. And when there is a displaced fluid flow starting, that is analogous to the energy stored in the capacitor. So we can take this analogous to understand the two techniques. Now if we see some commercial available capacitors, so these capacitors, lot of capacitors are available in the market depending upon the applications. And in electrical lab, we use the capacitors for doing different experiments. So there are some capacitors for figure A. So left to right, if we go, we get 270 picofarad ceramic capacitors, 20 microfarad tantalum, 15 nanofarad polyester, and 15 nanofarad polyester. So you can see that these capacitors, which capacitors are very small capacitors, whose values lie in picofarad, microfarad, and nanofarad. This figure, you can see that there is a 40 volt DC electrolytic capacitor of 200 microfarad, whereas there is a 25,000 microfarad 35 volt DC electrolytic capacitors. So these capacitors are big capacitors which are in the range of 2000 microfarad. Now here you have some capacitors which are electrolytic and of different ranges. Now with this commercial capacitor, you can see that 1 farad, which is the unit of a capacitor, is quite big. This value of the capacitor 1 farad is quite big, but actual commercial capacitors are used in the range of picofarad, microfarad, or nanofarad. Farad is basically a very bigger unit of the capacitance, but commercially when we take some capacitor, it will be in the range of picofarad or microfarad, nanofarad range. Let us discuss some important properties of a capacitor. So when the voltage across a capacitor is not changing with time, that is a DC voltage is applied, the current through the capacitor is zero. It means that for a capacitor which is applied to a DC quantity, so if you applied a DC source plus minus DC to a capacitor, now since you know that the DC is constant and there is no variation with respect to time, so the current which is flowing through the capacitor is basically zero. So we can say that a capacitor is open circuit to DC. So we can do like this. There will be an open circuit condition when we apply a DC source to the capacitor. However, if we apply a DC voltage using a battery, then the capacitor will start charging. Current will be zero. Current will not flow, but the capacitor will charge itself. The voltage on a capacitor cannot change abruptly. This is a very important point. When you apply a voltage through a capacitor, the voltage will not change abruptly. It will be very slowly change in the capacitor. When we talk about an ideal capacitor, it does not dissipate energy. It takes power from the circuit, stores energy in the field, and then return the stored energy when delivering power to the circuit. But the dissipating energy is equal to zero for an ideal capacitor. Whereas when we talk about a real non-ideal capacitor, there will be some amount of losses. So these loss will be represented with a parallel mode leakage resistance. So you have a capacitor, you connect a resistance in parallel to represent the loss in the capacitor in the form of a leakage resistance. Typically, the value of this leakage resistance is very high, around in the range of 100 mega ohms, and therefore in all practical applications this will be neglected because there will be no current flowing here in the resistance. Because the resistance is very high, current will be less, and practical applications you can remove it as if it is an ideal capacitor. So here we can see that the two conducting plates separated with a dielectric and the magnetic electric flux lines are being shown. So if the capacitor is ideal and all the flux lines, electric field lines are basically present in the dielectric, then there will be no leakage. However, if the capacitor is non-ideal and the electric field lines are not concentrating only in the dielectric but rather coming out in the air, then that phenomena is known as fringing effect. And the loss in the capacitor is represented with the resistance which is connected in parallel with the capacitor. So this is the ideal capacitor, and the resistance is connected in parallel to represent that this is a non-ideal capacitor or a real capacitor. There is some loss. So we'll discuss the stored charge and current in terms of voltage for a capacitor. So you know that in an ideal capacitor, the stored charge Q is proportional to the voltage between the plates. So you have a parallel plate capacitor. This is the dielectric. So the charge is given by capacitance multiplied with the voltage. So whatever the voltage is applied, the stored charge is basically capacitance into voltage. This is the most fundamental equation. Now here the C is basically the constant of proportionality, which is known as the capacitance of the capacitor. The unit is Farad and it is equivalent to Coulomb per volt because C is equal to Q by V. So we can see that Q unit is in Coulomb and voltage unit is in volt. So 1 Farad is equal to 1 Coulomb per volt, we can say. Now if we recall that current is the time rate of flow of charge. So dq by dt, we know I is equal to dq by dt. So if we differentiate the charge with respect to time, then we get d by dt of cv, and c is a constant of proportionality. So we can take c outside the differential. So we get I is equal to c dv by dt equation. So this is our capacitor. Due to the application of the voltage with this time varying as a function of time, then there is a flow of the current which is also time varying. Now since the capacitor is a passive element, it will store the energy, not dissipate energy. Also the current entering terminal will be positive and current leaving terminal will be negative. So the current is entering this terminal, so it will be positive. Current is leaving this terminal, so it will be negative. If the voltage source is applied opposite, so the current is moving in this direction, so this will be positive and this will be negative. So we have to take proper sign convention of the current. Capacitance is not a function of time. That we can see that capacitance has been taken outside and not a function of time. Now when the voltage increases, so this capacitor, when you apply the voltage, so this voltage is applied, the current flows through the capacitor will also increase and charge will accumulate on each plate. So there will be accumulation of the charge in each plate. You have seen the positive charge and the negative charge. However, if the voltage remain constant, now what will happen? That voltage is not the function of time. So charge is also constant and current will zero. So this current will be 0 for the DC voltage. So when DC voltage is applied, current will be 0, but it will charge itself. Thus, a capacitor appears to be open circuit for a steady DC voltage. So whenever you apply a steady DC voltage, you will see that there will be an open circuit of the capacitor for the DC voltage. However, it will start charging. Current flow will be 0. This phenomena is very important to understand, and when we study the transient analysis, we will use this again and again. So we'll discuss the voltage in terms of current now. Now computation of charge and voltage for a known current. First what we have done, we have taken from voltage to current. Now what we do is that if we know the current, what is the corresponding voltage and the charge, that we are going to study for the capacitor. Let us see the equation. So you have seen that the current is basically C dV by dt, where voltage is the variation of time. The fundamental equation of charge Q by Q of t is integrating from some initial time t0 to the final time t, I of t dt, where there is some initial charge already present, Q of t0. So these fundamental equation, if we use and determine the voltage which is there for the capacitor for a known current, so we get the voltage equation as 1 by C integral I dt from t0 to t, and there is some initial voltage. So the initial voltage at time t0 is equal to the charge at time t0 divided by the capacitance. So this will be equated. The voltage at time t0 is equal to the charge at time t0 divided by the capacitance value. So we can use the fundamental equation to compute the charge and voltage for the known current. What is the stored energy in the capacitor? Can we know that? Now consider that a capacitor is initially having no voltage. So there is no voltage in the capacitor. Then the initial stored electrical energy is also 0. And we say that the capacitor is uncharged. So if there is no voltage initially, there is no energy and the capacitor is uncharged. Then in that case, we can write the equation of the energy starting from the derivation of power. So power is the product of voltage into current, that we know. But these are time varying quantities. Power is basically CV dV by dt that we can obtain. And energy is basically integral of power from T0 to T. So if we integrate the power equation, we get CV dV by dt into dt of dt. So now we can get Wt is equal to integral from 0 to Vt CV dV, because your dt and dt will cancel out each other and you will get CV dV. It means that the energy is equal to half CV square. So this, when integrating, you will get half CV square. Also, if we write from the equation Q is equal to CV and we write in terms of charge, then we get Q square by 2C is also the energy. So energy equation, you have to remember that half CV square is the energy stored in the capacitor, or this is equal to Q square by 2C. So this is the energy stored in the capacitor. Now, capacitance can be connected either in series or parallel. First, let us see if the capacitance is connected in parallel, what is happening and what is the equivalent capacitance. Similarly, what we have done for the resistance. So we have taken an example of three capacitors C1, C2 and C3, which are connected in parallel with a voltage source. And you know that when there is a parallel connection, the current will divide among the capacitors for the source current I. And we will derive that the C equivalent is equal to C1 plus C2 plus C3 and so on for the nth capacitor. So when the capacitors are connected in parallel, all the capacitors will be added up to find the total equivalent capacitance. How we can derive that? First, we will find out the individual current through each capacitor. So you know that I is equal to C dV by dt. Voltage remain constant for all the parallel connection. There is only division of the current. The capacitor values are different, C1, C2 and C3. Now, The KCL equation is summation of the current is the total current. So I1 plus I2 plus I3 is the total current. Now if we put the values of I1, I2 and I3 to the current equation, taking the common dV by dt which is constant, we get C1 plus C2 plus C3. It means that the C equivalent is C1 plus C2 plus C3. So the net current which is flowing through the source from the source is basically C equivalent dV by dt. So if you remember the resistance, this is opposite. So if you see the resistances in parallel form like this. So this is opposite of the resistance. So if you remember the resistance property, you can take that example for the capacitance property. Now, if the capacitances are in series, then what will happen? N number of capacitors are connected in series. So there will be a voltage division within the capacitor. Now, this circuit can be represented with a single C equivalent and flowing of the current. So there, what is the voltage for that capacitor? So voltage distribution will be there when there is a series capacitor, because when you have the parallel capacitor, there was a current division. Here you have the voltage division. Now you know that the voltage equation is 1 by C integral IDT with some initial value. Okay, so if we put that equation in V, that is V equal to V1 plus V2 plus V3 to Vn, and V1 equation we put 1 by C1 integral T0 to T IT dt plus V1, and similarly for V2 and similarly for Vn, and we take all the initial values outside and the capacitance common to the current IT dt, because for a series circuit the current will remain the same, because it is a series circuit, current will remain the same. Then this value we can substitute as 1 by C equivalent integral of I dt plus the initial value of the voltage, which is this one, for individual capacitor. It means that the 1 by C equivalent is equal to 1 by C1 plus 1 by C2 plus 1 by C3 to 1 by Cn. If you remember this is resistance in parallel, similar to resistance in parallel. So resistance in parallel will behave as capacitor in series, and capacitance in parallel will behave as resistance in series. So this is all about the discussion on the capacitors, which is a very important part, and afterwards we will discuss what is the property of inductance.